You know, people always ask me why magnets work, and I have to tell them something that might sound like I'm dodging the question, but I'm really not. The problem is that the question itself, why do magnets work, assumes that I can give you an answer in terms of something you're already familiar with, and I can't. Not really. Because magnetism is one of those deep, fundamental things in nature that doesn't come from something else more familiar. It just is. Now, I know that sounds like a cop-out, so let me try to explain what I mean by that, and maybe by the end, you'll see why this question is so much stranger than you think. When you ask why something happens, what you're really asking is, can you explain this thing in terms of something I already understand? Like if you ask me why ice floats, I can tell you that water molecules spread out when they freeze, so the ice is less dense than the liquid water, and less dense things float. You understand density, you understand floating, so that answer works. But what happens when you get to something really fundamental, something that doesn't reduce to anything simpler? Then I'm stuck. I can't explain magnetism in terms of something more familiar because there isn't anything more familiar. It's already at the bottom. But let me try anyway, because even though I can't give you the kind of answer you want, I can at least show you what's really going on, and it's so much weirder than you think. First thing you need to understand is that magnetism isn't separate from electricity. They're the same thing, two sides of the same coin. We call it electromagnetism, and that's one of the 4 fundamental forces in nature. When you wave a magnet around, when you stick one on your refrigerator, you're experiencing 1/4 of all the forces that exist in the universe. That's pretty remarkable if you think about it. Now here's where it gets interesting. You've got this electron sitting there in an atom, and it's got a property we call spin. Now spin is a terrible word for what's actually happening because the electron isn't actually spinning like a little ball. It's a quantum mechanical property that has no classical analog, but it acts like the electron is a tiny magnet. Every single electron in the universe is like a microscopic bar magnet. They've got a north pole and a south pole, and they create a magnetic field around them. That's just what they do. Why do they do that? Well, that's like asking, why does an electron have charge? It just does. That's what an electron is. So you've got all these electrons in a piece of material, and they're all these tiny magnets pointing in different directions. In most materials, like wood or plastic or your hand, these little electron magnets are all jumbled up, pointing every which way, so they cancel each other out and you don't get any net magnetic field. But in certain materials, like iron or nickel or cobalt, something special happens. These electrons can line up. They can all point in the same direction. And when billions and billions and billions of these microscopic magnets all point the same way, you get a magnet, a real macroscopic magnet that you can hold in your hand. But why do they line up? This is where quantum mechanics comes in, and this is where things get really strange. There's this thing called the exchange interaction, and it's purely quantum mechanical. There's no classical explanation for it at all. It comes from the Pauli exclusion principle, which says that 2 electrons can't be in the exact same quantum state. Now, what does that have to do with magnetism? Everything, because it turns out that when electrons in neighboring atoms have their spins aligned pointing the same direction, they can stay a little bit farther apart from each other, and when they're farther apart, their electric repulsion is a little bit less. And that lower energy state, that's more stable, so the electrons want to align their spins. Think about that for a second. Magnetism, this thing where pieces of metal stick together, comes from the fact that electrons are fermions that obey the Pauli exclusion principle combined with their quantum mechanical spin. If electrons were a different kind of particle, if they didn't have this half-integer spin, if they didn't obey Fermi-Dirac statistics, magnets wouldn't exist. The refrigerator magnets in your kitchen exist because of deep quantum mechanical principles that govern the behavior of identical particles. That's astounding. But there's more. Let me tell you about magnetic fields, because this is where your intuition really breaks down. You might think of a magnetic field as some kind of stuff, some kind of medium that fills space around the magnet. But it's not stuff, it's a field. And fields are one of the most important concepts in all of physics. A field is just a number, or in this case, a vector, assigned to every point in space. At every single point near a magnet, the field has a value and a direction. That's it. It's just a mathematical description of how space itself has been modified by the presence of the magnet. Now here's the kicker. When you put another magnet in that field, it experiences a force. Why? Because that field affects the electrons in the second magnet. The field pushes on those tiny electron magnets, trying to align them or anti-align them depending on the orientation. And that push, that interaction between the field and the matter, that's what you feel as the magnetic force. But what's really doing the pushing, the field, And what is the field? It's just a convenient mathematical description we invented to calculate forces. Does the field really exist, or is it just a bookkeeping device? That's a deep question, and I'm not sure there's a right answer. Let me come at this from another direction. Maxwell figured out in the 1800s that electricity and magnetism are deeply connected. If you move an electric charge, you create a magnetic field. If you change a magnetic field, you create an electric field. They're intertwined in this beautiful way that Maxwell described with his equations. And when you solve those equations, you find that electromagnetic disturbances, waves in the electric and magnetic fields, propagate through space at a particular speed. And that speed, it turned out to be the speed of light. Light is an electromagnetic wave. Think about that. When you see something, when light enters your eye, that's oscillating electric and magnetic fields propagating through space. Vision is an electromagnetic phenomenon. Color is just different frequencies of electromagnetic waves. Everything you've ever seen is electromagnetism. But we can go deeper still. Einstein showed us that magnetism is really just electricity viewed from a moving reference frame. If you're at rest with respect to a charged particle, you see an electric field around it. But if you're moving relative to that charged particle, you also see a magnetic field. The magnetic field appears because of relativistic effects, because of the way space and time mix together when you're moving. In other words, magnetism is a relativistic correction to electricity. If the speed of light were infinite, if there were no relativity, there would be no magnetism. The magnets on your refrigerator exist because the speed of light is finite, because we live in a relativistic universe. How's that for shattering your reality? Now let's talk about quantum field theory, because that's the deepest description we have. In quantum electrodynamics, QED, we describe the electromagnetic force as the exchange of virtual photons. When two electrons repel each other, when two magnets push apart, what's really happening at the quantum level is that they're exchanging photons back and forth. These aren't real photons that you could detect. They're virtual. They exist only for the brief instant allowed by the uncertainty principle. But they're what carry the force. The electromagnetic field, in this picture, is made up of quantum fluctuations, virtual particles constantly popping in and out of existence. The vacuum, empty space, isn't empty at all. It's seething with activity with these quantum fluctuations. And when you move a real charge through this quantum foam, it interacts with all these virtual particles. And that interaction is what we call the electromagnetic field. So when you ask why magnets work, I have to tell you it's because electrons have spin, because they obey the Pauli exclusion principle, because the exchange interaction lowers the energy when spins align, because electromagnetic fields satisfy Maxwell's equations, because we live in a relativistic universe where space and time are connected, because quantum mechanics allows virtual photons to mediate forces, because the structure of space-time and the properties of quantum fields are what they are. And if you ask why those things are the way they are, I can't tell you. That's where physics stops. We've described nature as deeply as we can right now, but we haven't explained why nature chose these particular rules. Maybe someday we'll have an even deeper theory that explains why the laws of physics are what they are, why the constants have the values they do, why electrons have the mass and charge and spin that they have. But until then, we're stuck with this fascinating situation where the deeper you dig, the more you find that the familiar world emerges from utterly strange quantum mechanical and relativistic principles that have no counterpart in everyday experience. Your intuition, built up from a lifetime of experience with medium-sized objects moving at slow speeds, completely fails at the atomic level. And magnets, these common everyday objects, are a window into that alien quantum world. Let me give you one more way to think about this. You know how when you try to push two magnets together the wrong way, they resist, they push back. You can feel that force in your hand. Now your hand, your muscles, are made of atoms held together by chemical bonds, and chemical bonds are electromagnetic. They're electrons being shared between atoms. So when you push on the magnet, your electrons are pushing on the magnet's electrons through electromagnetic forces. But those forces are carried by virtual photons in the quantum field theory picture. So what's really happening is that virtual photons from your hand are interacting with virtual photons from the magnet, and the quantum mechanical amplitude for all the different ways this can happen adds up to give you the force you feel. You are directly experiencing quantum field theory with your bare hands. Every time you stick a magnet on your refrigerator, you're doing a quantum mechanics experiment. You're seeing the macroscopic consequence of the Pauli exclusion principle, of electron spin, of the gauge symmetry of electromagnetism, of all these deep principles of nature. And the craziest part is that all of this, all of quantum electrodynamics, is one of the most precisely tested theories in the history of science. We can calculate things like the magnetic moment of the electron, how strongly the electron acts as a tiny magnet, and we can measure it, and they agree to something like 10 decimal places. That's like predicting the distance from New York to Los Angeles to within the width of a human hair. The theory works. It's not just mathematical speculation, it's been confirmed to outrageous precision. So when I tell you that magnetism comes from quantum mechanical spin and the exchange interaction and virtual photons, I'm not making it up, I'm not being poetic. That's really how nature works, as far as we can tell. But here's what really bothers people when I explain all this. They want to know the mechanism. They want to know how it works in terms of little balls and springs or gears or something they can picture. And I have to tell them that nature doesn't work that way at the fundamental level. There are no gears, there are no springs, there's just the mathematics of quantum field theory and the wave functions and the operators and the symmetries. And when you calculate with all that, you get predictions that match experiments. That's all we have, and that's all we can ask for. Physics doesn't tell you what things are really made of, it tells you how things behave, how to predict what will happen in an experiment. The map is not the territory, and the equations are not the reality, they're just our best description of reality. So when you ask me why magnets work, I can tell you the whole story. I can tell you about electron spin, and exchange interactions, and Maxwell's equations, and virtual photons, and gauge symmetries. But at the end of the day, if you ask me why nature is quantum mechanical, why charges create fields, why the universe has the particular symmetries it does, I have to say I don't know. That's just the way it is as far as we can tell. And maybe that's not satisfying, maybe you wanted a deeper answer, but that's the honest truth. Science can take you incredibly far down into the structure of reality. It can show you things more bizarre than you ever imagined, but eventually you hit bedrock, you hit the fundamental laws, and there's no deeper explanation available, at least not yet. And you know what? I think that's beautiful in its own way. We live in a universe governed by quantum mechanics and relativity, by symmetries and conservation laws, by principles that are utterly alien to our everyday experience, but that work with extraordinary precision. And those principles give us magnets, they give us light, they give us chemistry and biology, and ultimately us conscious beings who can discover these laws and marvel at them. The fact that we can understand any of this at all, that we can write down equations that describe how magnets work, that's the real miracle. The universe didn't have to be comprehensible, but it is, at least partly. And every time you play with a magnet, every time you feel that invisible force pushing or pulling, you're experiencing something truly fundamental about nature, something quantum and relativistic and deeply strange. That's why magnets work, and that's why the answer might shatter your reality, because reality is so much weirder and more wonderful than we have any right to expect.